Hello, my friend. If you have trouble falling asleep, you are in the right place. Few ideas in modern science feel as vast, strange, and quietly thrilling as the possibility that our entire universe may be only one version of reality. In some multiverse ideas, there could be many versions of you, each existing in a different branch of reality, living its own version of life, making choices you never made, and experiencing what you never will. It is the kind of idea that sounds like pure fiction at first, yet it appears again and again whenever physicists push their best theories toward the deepest questions about existence. So if your mind is restless and sleep feels far away, you are in exactly the right place, because tonight we are going to let one of the biggest ideas in science slowly unfold around you. Chapter 1. Why the idea of the multiverse exists at all. The multiverse is not a single theory, and it is not a scientific fact that has been established in the way that Earth's orbit around the sun has been established. It is better understood as a family of serious ideas that appears when physicists try to follow some of their best theories farther than direct observation currently allows. In other words, the multiverse was not invented simply because scientists wanted a dramatic story about parallel worlds. It emerged because several major efforts to explain the universe seem, at least in some versions, to point beyond the boundaries of the one cosmic domain we can observe. To understand why the idea appeared at all, it helps to begin with a simpler point. Physics does not only describe what exists in front of us. Very often, it asks what must be true if the patterns we observe are taken seriously and extended consistently. This is how modern science learned that stars are powered by nuclear processes, that galaxies exist far beyond the Milky Way, and that space itself is expanding. In each case, the theory reached farther than ordinary human intuition, and observation later caught up, at least in part. The multiverse enters science in a similar spirit. It is not the first guess one makes about reality. It is what remains on the table when certain powerful ideas are pushed to their logical limits. One reason the multiverse became hard to ignore is that our universe looks strangely well suited for structure. Matter can clump. Stars can shine for long periods. Chemistry can become rich and complicated. In at least one tiny corner of the cosmos, life can emerge and ask questions about the whole arrangement. Physicists and philosophers have long noticed that many features of the universe appear delicately balanced in ways that matter for this outcome. This observation is often called fine-tuning. The term does not mean that science has proved the universe was designed. It means that some of the constants and conditions in our best physical descriptions seem to fall within ranges that permit complex structure, and that this fact demands some kind of explanation, or at least some careful interpretation. Once that problem is noticed, several possibilities present themselves. Perhaps there is only one universe, and there is some deep principle that forces the constants of nature to take exactly the values they do. Perhaps the values were set by an as yet unknown final theory that leaves no room for alternatives. But another possibility is that reality contains many cosmic domains with different conditions across them, and we naturally find ourselves in one of the regions where observers can exist. This line of thought is closely related to what is called the Anthropic principle in its weaker and more scientifically modest form. The idea is not that the universe was made for us. The idea is that any beings capable of noticing the universe will necessarily observe conditions compatible with their own existence. In a sufficiently varied multiverse, that selection effect becomes one possible explanation for why our universe looks unusually hospitable. A second route to the multiverse comes from cosmology, especially from inflation. Inflation is the name given to a hypothesized burst of extremely rapid expansion in the early universe. According to NASA's overview of cosmic history, cosmologists use inflation to explain important large-scale features of the universe, including its striking flatness. NASA's education materials also note that inflation was introduced in part to address the horizon problem by proposing that a small region of space expanded enormously in a very short interval. On its own, that already stretches the imagination, but some versions of the theory go further. In eternal inflation models, inflation does not end everywhere at once. It continues in some regions while stopping in others, allowing separate bubble-like universes to form within a still inflating background. Under those conditions, what we call our universe would be only one local pocket in a much larger inflating reality. This matters because inflation was not originally designed as a machine for generating multiple universes. It was proposed to solve specific problems in early universe cosmology. The multiverse appears as a possible consequence of trying to make that framework mathematically and physically complete. That is one of the main reasons many physicists take the idea seriously, even while remaining cautious about it. When a speculative picture grows out of a theory that was motivated by other explanatory successes, it earns a different kind of attention than a purely free-floating fantasy. At the same time, careful scientists also emphasize that inflation is a research program with unresolved questions, and that not every model of inflation implies the same larger picture. So even here, the scientific attitude is balanced. The multiverse is suggested by some influential ideas, but it is not confirmed by direct observation. A third route to the multiverse emerges from quantum mechanics. Quantum theory is extraordinarily successful in predicting the behavior of matter and radiation, but it raises deep questions about what a measurement really means. One interpretation, associated with Hugh Everett, suggests that the wave function does not collapse in the ordinary sense. Instead, all allowed outcomes continue to exist in different branches of reality. CERN materials discussing the many worlds picture describe it as a view in which the world we experience is constantly branching into different versions, corresponding to different measurement outcomes. If that interpretation is correct, then the multiverse is not mainly about distant bubbles in cosmic space. It is about the structure of quantum reality itself. The world would contain many coexisting branches that no longer interfere with one another in any practical way. Here again, the important point is not that physicists casually decided to multiply worlds for dramatic effect. The many worlds idea arose from a very specific effort to take the mathematics of quantum mechanics seriously without adding a special collapse rule. Whether that is the best interpretation remains debated, and there is no universal agreement among physicists. But its importance in the history of multiverse thinking is undeniable. It showed that the idea of many worlds could emerge not only from cosmology, but also from the foundations of quantum theory. That made the multiverse harder to dismiss as a single strange speculation living at the edge of astronomy. It began to appear as a recurring possibility in more than one area of fundamental physics. There is also a more theoretical reason the multiverse remained attractive. Physicists often hope that the laws of nature are not arbitrary. They want to know why these particles exist, why these constants have these values, and why the universe began in a state able to generate galaxies, stars, planets, and chemistry. But as modern theories became more ambitious, especially in high-energy physics and cosmology, they sometimes produced not one possible world, but many. In discussions of fine-tuning, the Stanford Encyclopedia of Philosophy notes that when ideas from inflation are combined with the string theory landscape, one obtains a picture in which many distinct vacuum states, corresponding to different higher-level laws or constants, could be realized in different island universes. That kind of framework does not prove a multiverse exists. It does show why the idea keeps returning whenever theorists search for a deeper account of physical law. At this point, it is important to say what the multiverse is not. It is not a settled map of reality. It is not one clearly defined object that science has measured. It is not even one unanimously accepted concept. The word covers several different proposals, some tied to inflation, some to quantum mechanics, and some to deeper speculative theories such as string theory. These proposals are motivated by different problems and operate in different ways. That is why serious discussions of the multiverse are usually cautious. Scientists who take it seriously do not all mean the same thing by it, and many scientists remain skeptical precisely because some multiverse versions are difficult to test directly. Criticism is not a side issue here. It is part of the subject itself. A scientifically responsible view begins by admitting that the multiverse is an open question, not a final answer. And yet the idea persists because it touches a genuine scientific pressure point. Again and again, modern physics seems to confront us with a choice. Either there is a deeper necessity that uniquely fixes the form of our universe, or what we call our universe is one realized possibility among many. The multiverse is compelling because it offers a way to think about contingency. Why these constants rather than others? Why this cosmic history rather than another? Why a universe able to host long-lived stars, rich chemistry, and questioning minds? It may turn out that future physics explains all of this within a single universe framework. It may turn out that the multiverse remains too flexible to count as a satisfying explanation. But the reason the idea exists at all is clear. It was born from the attempt to make sense of real scientific puzzles, not from a desire to decorate the cosmos with fiction. There is something quietly humbling in that. The multiverse reminds us that the universe we know may not be the measure of all that exists. It reminds us that science, at its best, is willing to follow evidence and theory even when the destination feels larger than comfort allows. For now, no one needs to force a conclusion. It is enough to see why the question appeared, why thoughtful people take it seriously, and why it remains unresolved. Let that uncertainty feel gentle rather than heavy. Tonight, you do not need to solve the cosmos. You only need to rest beneath it and let your mind grow still while the larger questions keep their patient watch above you. Chapter 2. Why our universe seems strangely fine-tuned for life. When scientists say that our universe appears fine-tuned for life, they do not mean that physics has proven the universe was intentionally designed for living beings. They mean something more precise and in a way more unsettling. They mean that the basic structure of reality seems to depend on a set of conditions that lie within a fairly narrow life-permitting range. If some of those conditions had been meaningfully different, the universe might still have existed, but it may have been too simple, too short-lived, too chaotic, or too sterile to produce long-lived stars, complex chemistry, planets, and eventually observers capable of asking where they came from. In philosophy of physics, fine-tuning refers to this sensitive dependence of important outcomes on the values of underlying parameters and laws. This idea became important because modern physics does not describe the universe only in general poetic terms. It describes nature using quantities, interactions, symmetries, and initial conditions. Some of these are built into the structure of our theories as measured constants, rather than values derived from deeper principles already known to us. That matters because if certain constants had taken different values, the resulting universe might have unfolded very differently. Fine-tuning, then, is not the claim that life was guaranteed, nor the claim that life was the purpose of the cosmos. It is the more careful observation that the kind of universe capable of building stable complexity may occupy only a limited region within a larger space of physical possibilities. That is why the subject keeps returning in cosmology, particle physics, and philosophy of science. One of the clearest places to begin is gravity. Gravity is the weakest of the known fundamental interactions at the level of elementary particles. Yet on large scales, it dominates the architecture of the cosmos because it is always attractive and acts across enormous distances. If gravity were significantly stronger, matter in the early universe could have collapsed too quickly, changing how stars formed and evolved. Many stars might have burned through their fuel too rapidly or collapsed under their own weight before long. Stable eras of stellar light could support complex chemical development around them. If gravity were much weaker, matter would have had more difficulty gathering into stars and galaxies in the first place. In both directions, the large-scale story of the universe could lose the long quiet periods that make cosmic complexity possible. Fine-tuning arguments do not depend on drama here. They depend on the fact that structure formation is sensitive to the strength and balance of physical processes. The electromagnetic interaction also matters profoundly. It governs the behavior of atoms, chemistry, light, and the structure of matter on everyday scales. If its strength were substantially different relative to other interactions, atoms might not hold together in the same way. Electron energy levels would shift, and chemistry as we know it could fail to support the wide variety of stable bonds needed for complex molecules. Life, at least in any form resembling biology based on rich chemical organization, depends on a universe where atoms are neither too fragile nor too rigid, neither too unstable nor too inert. The strong nuclear interaction adds another layer to this balance because it helps bind protons and neutrons inside atomic nuclei. If that balance changed too far, many familiar elements could not form reliably, and the chemical richness on which stars, planets, and life depend would be radically reduced. Fine-tuning is therefore not about one magical parameter. It is about interlocking physical conditions that together allow enduring structure. This becomes even more striking inside stars. Stars are not just bright objects scattered through the dark. They are long-running engines that turn simple early matter into heavier elements. Inside them, hydrogen can be fused into helium, and in later stellar generations, still heavier elements can be produced and spread into space. Carbon, oxygen, nitrogen, silicon, iron, and many other elements needed for planets and chemistry are tied to this stellar history. Fine-tuning arguments often point out that if the underlying nuclear and electromagnetic balances were meaningfully altered, stars might not shine in the same stable way. Heavy element formation could become much rarer, or the universe might end up filled mostly with simple ingredients and little else. This is one reason fine-tuning discussions are not merely abstract. They are tied to the fact that the periodic richness of matter depends on a universe able to run a long and delicate cosmic production process. Another famous example concerns the cosmological constant, or something very close to what is often associated with vacuum energy in cosmology. Observations show that the expansion of the universe is accelerating, and current cosmology commonly describes that acceleration using dark energy, often modeled as a cosmological constant. NASA's scientific summaries describe dark energy as the dominant component in the cosmic energy budget and note that it drives the accelerated expansion of the universe. The fine-tuning issue here is not merely that dark energy exists, but that its observed value is extraordinarily small compared with the kinds of much larger values that naive theoretical expectations might suggest. If the effective vacuum energy were much larger and positive, cosmic expansion could outrun the growth of galaxies and large structures before they had time to form. If it were large in the opposite direction, cosmic evolution might collapse too quickly. Whatever the deeper explanation turns out to be, the observed value seems peculiarly compatible with a structured universe. The early universe also appears to have begun in a remarkably special state. Modern cosmology shows that the observable universe is close to spatial flatness on large scales, and that distant regions share a striking level of large-scale uniformity. These features helped motivate inflation, the idea that the early universe went through a brief period of extremely rapid expansion. NASA explains that inflation helps account for why the universe appears so flat, and why regions now far apart could once have been close enough to share common physical conditions. Fine-tuning enters here because without some mechanism of this kind, the early universe seems to require very special initial conditions to produce the large, smooth, structured cosmos we inhabit. Inflation may help explain some of that apparent specialness, but it also shifts the question rather than erasing it completely. One may then ask why the inflationary conditions themselves were suitable, or whether inflation produces many cosmic regions with different properties. It is important, however, not to overstate what fine-tuning means. Scientists are not all saying the same thing when they use the term. Sometimes it refers to the sensitivity of cosmic habitability to changes in constants. Sometimes it refers to the unnatural appearance of a parameter inside a theory, meaning that its value seems surprisingly small or delicately balanced relative to what the theory might have allowed. Sometimes it refers to the initial conditions of the universe. These are related ideas, but they are not identical. A careful scientific treatment keeps them separate. The fine-tuning of the cosmological constant, for example, is not exactly the same issue as the conditions needed for carbon chemistry, even though both contribute to the broader question of why the universe permits complex structure. Keeping these distinctions clear matters because otherwise the conversation becomes more dramatic than accurate. There is also an important scientific caution built into the whole subject. Fine-tuning arguments often imagine changing one parameter while holding many others fixed, but a deeper theory of nature might reveal that these quantities are not independent after all. Some values that now look arbitrary might eventually turn out to be linked by a more fundamental framework. In that case, what appears as fine-tuning today could someday look like a natural consequence of deeper laws. This is one reason the subject remains open rather than settled. Physicists do not merely ask whether the universe looks special. They also ask whether its apparent specialness reflects real contingency or only our current ignorance of a more unified theory. The existence of a puzzle does not guarantee the truth of any particular solution. It only means the puzzle deserves serious thought. Still, the impression of fine-tuning is hard to dismiss completely because the universe does not merely allow isolated simplicity. It allows layered complexity over immense stretches of time. It allows stars to live long enough to seed galaxies with heavier elements. It allows chemistry to become subtle. It allows planets to persist. It allows conditions under which information can be stored, copied, and acted upon. It allows biological evolution to operate in a cosmos that is not instantly hostile to every organized structure. None of this proves that life was inevitable, and none of it proves that there are many universes. But it does make the universe look unusually generative. It looks like a place where the laws of nature do not merely permit existence in the barest sense, but permit the gradual emergence of richness. That is exactly the observation that later chapters will connect to anthropic reasoning and multiverse ideas. This is why fine-tuning became such a central doorway into multiverse thinking. If there is only one universe, then one hopes for a deep reason why its constants and conditions take life-permitting values. But if reality includes many cosmic regions, each with different realized parameters or effective laws, then it becomes less surprising that at least some regions would support observers. In that picture, we do not live in a special universe because the cosmos as a whole was arranged around us. We live in a special universe because only a special kind of universe can ever be noticed from the inside. That does not settle the question. It only changes the style of explanation. The fine-tuning problem remains one of the reasons the multiverse is treated as more than science fiction. It is an attempt, whether successful or not, to answer a real scientific tension. And perhaps that is what makes the subject feel so quietly powerful. The laws of nature are vast and impersonal, yet somehow they have unfolded into a universe where matter can become stars, stars can become chemistry, and chemistry can become a mind listening in the dark. Whether that happened by necessity, by selection, or as one branch among many possibilities, the fact remains strangely beautiful. You are part of a universe delicate enough to wonder about itself. And as the day finally loosens its grip, you can let that thought become gentle. Out of all the silence, reality became ordered enough for consciousness, and for one brief moment, it became you. Chapter 3. The Anthropic Principle and Why We Observe This Kind of Universe. The Anthropic Principle sounds at first far more mystical than it really is. In serious scientific discussion, it is not a claim that the universe was made for us, and it is not a magical explanation that solves every cosmic mystery by placing human life at the center of reality. At its most careful and defensible, it is a reminder about selection effects. It tells us that any universe observed by beings like us must, at the very least, be compatible with the existence of observers. That may sound obvious, even trivial, but in cosmology, obvious truths can become surprisingly powerful when they are ignored. The anthropic principle matters because it changes how we interpret the fact that we find ourselves in a universe capable of producing structure, chemistry, planets, and consciousness. It asks us to remember that our location in reality is not random in the simplest possible sense. We do not observe just any imaginable universe. We observe a universe in which observers can arise. This way of thinking entered modern cosmology partly as a reaction against the temptation to treat our observations as though they were drawn from all logically possible worlds without restriction. The astrophysicist Brandon Carter gave the anthropic principle its best-known name and formulation, building on earlier reasoning by Robert Dicke. Dicke had already pointed out that the age of the universe observed by living beings could not be completely arbitrary. If the cosmos were much younger, many of the heavier elements needed for rocky planets and complex chemistry would not yet have been widely available. If it were vastly older, large populations of stars suitable for stable planetary environments would have changed, and many of the conditions associated with biological development could become rarer. Carter's contribution was to emphasize that our observations are necessarily filtered by the conditions required for observers to exist at all. That sounds modest, and it is. But modest principles can still reshape the logic of explanation. To see why, imagine asking a question in the wrong way. Suppose someone looks at the universe and says that it is astonishing we happen to live in a cosmos with long-lived stars, stable atoms, rich chemistry, and cosmic history stretched across immense spans of time. That reaction is understandable. But the anthropic principle answers by saying that there is a hidden bias in the question. A universe without such features would not contain observers wondering why those features exist. In other words, the fact that we observe a life-permitting universe cannot be treated as though it were a neutral surprise drawn from all possible physical realities. Our existence as observers already places a filter on what can be observed. The anthropic principle does not remove the mystery entirely, but it does change the kind of mystery we are dealing with. This is why the anthropic principle is often described as an observation selection effect. The key word here is selection, though not in the biological sense of natural selection. It means that the conditions of observation select which parts of reality can ever become objects of experience. This idea appears in many areas of science. We are often forced to correct for biases introduced by the fact that certain outcomes are easier to detect than others. In cosmology, the bias is even deeper because it concerns the existence of the observer rather than the limits of an instrument. We are not merely correcting for what a telescope can see. We are correcting for the fact that any observed universe must allow the emergence of the very beings doing the observing. The most restrained form of anthropic reasoning is usually called the weak anthropic principle. Despite the name, weak here does not mean unimportant. It means cautious. It states, in effect, that the observed values of physical conditions must be compatible with the existence of observers in the place and era where observation occurs. This principle does not claim that the universe had to produce life, nor that life is the goal of cosmic evolution. It simply says that once observers exist, their observations cannot be detached from the conditions that made them possible. In this form, the anthropic principle is not really a new physical law. It is more like a warning against drawing naive conclusions from incomplete reasoning. There are stronger versions of the anthropic principle, and these are much more controversial. Some formulations suggest that the universe must in some sense give rise to life, or that conscious observers play a deeper necessary role in cosmic existence. These stronger statements move well beyond the modest selection effect that most scientists are comfortable discussing. They risk becoming teleological, meaning they can sound as though the universe is directed toward an end or purpose. That is precisely where many physicists and philosophers become cautious. The scientifically useful part of anthropic reasoning does not require such claims. It is enough to say that observed conditions are constrained by the existence of observers. That is already a meaningful point, and it avoids turning a methodological insight into a metaphysical proclamation. The real importance of the anthropic principle becomes clearer when it is connected to fine-tuning. In the previous chapter, the question was why the universe appears to fall within a range of conditions that permits complex structure and life. The anthropic principle does not by itself explain why those conditions exist. What it does is alter how we should interpret the fact that we observe them. If there were only one universe and its laws and constants were fixed uniquely by a deeper theory, then anthropic reasoning would mainly serve as a reminder not to be surprised that observers find themselves in observer-friendly conditions. But if there are many cosmic domains or many universes with varying conditions, then the anthropic principle becomes more than a warning. It becomes part of a possible explanatory framework. In such a setting, it may no longer be mysterious that at least some regions permit life. Observers would arise only in the rare domains where observation is possible, and naturally, those are the domains that get noticed. This is one reason the anthropic principle became closely connected to multiverse thinking. On its own, the principle is modest. Combined with a large ensemble of possible universes, it becomes much more ambitious. If many universes exist, each with different effective laws or constants, then our universe may not need to be typical in the broadest sense. It only needs to be typical among the subset of universes where observers can emerge. That distinction is crucial. Without anthropic reasoning, one might think our universe is astonishingly improbable in an unexplained way. With anthropic reasoning, one can say that improbable observer-friendly regions may still be exactly the regions from which observations arise. The improbability has not disappeared, but it has been reframed. A famous example of this kind of reasoning appears in discussions of the cosmological constant. The observed accelerated expansion of the universe suggests that empty space carries a very small but non-zero energy density. Many theoretical expectations once made it seem puzzling that this value is not vastly larger. If it were much larger in the positive direction, galaxies might never have formed before cosmic expansion pulled matter apart too quickly. In a multiverse setting, one possible anthropic response is that we should not be surprised to observe a vacuum energy small enough to allow galaxies, because observers require galaxies, stars, chemistry, and time. Steven Weinberg famously argued along these lines, using anthropic reasoning to estimate the order of magnitude within which such a constant might plausibly be observed if many universes with different values existed. Whether this counts as a deep explanation remains debated, but it showed that anthropic reasoning could do more than repeat a tautology. It could, under certain assumptions, help guide expectation. Even so, the anthropic principle has limits, and those limits matter. Many critics argue that anthropic reasoning can become too easy, too flexible, and too willing to accept what should instead be explained by deeper physics. If every puzzling parameter is answered by saying that otherwise we would not be here, then scientific explanation risks becoming lazy. This is one of the great tensions around the anthropic principle. Used carefully, it protects us from drawing false conclusions. Used carelessly, it can become a way of avoiding harder questions. That is why many scientists insist that anthropic reasoning should be a last resort rather than a first instinct. One should search for deeper dynamical principles, symmetries, or constraints before concluding that observer selection is the main explanation. There is another subtlety as well. The anthropic principle depends heavily on what counts as an observer and what conditions are truly necessary for life or intelligence. That is not always obvious. Much of the discussion assumes life forms at least broadly comparable to those known from our own universe, meaning entities built through stable complexity, energy flow, long-lived structure, and some form of information processing. But we do not know the full range of possible life. That uncertainty means anthropic claims must be made with care. A universe unsuitable for human biology is not necessarily unsuitable for every imaginable form of organized awareness. Still, even with that caution, some broad requirements seem difficult to escape. Observers of any interesting kind would likely need a universe with persistent structure, non-trivial complexity, and enough temporal stability for information-bearing systems to arise. What makes the anthropic principle so fascinating is that it stands at the edge between explanation and humility. It reminds science that observers are not outside the universe, looking in from nowhere. We are physical beings located within the system we are trying to understand. Our observations come from a very specific kind of cosmic environment, at a very specific stage of cosmic history, under conditions that are not automatically guaranteed in every conceivable world. In that sense, anthropic reasoning is not about inflating human importance. It does the opposite. It teaches us that even our ability to ask cosmic questions depends on a chain of physical preconditions, stretching back through stellar evolution, chemistry, and the earliest history of the universe itself. That is why the anthropic principle is both modest and profound. It is modest because it begins with something close to a truism. We can observe only a universe compatible with observers. But it is profound because that truism changes how we think about what needs explaining. It warns us that not every apparent coincidence is equally surprising once observer selection is taken into account. It also opens the door to a new style of cosmic reasoning, especially in the presence of a multiverse, where selection among many possible environments may matter as much as the underlying laws themselves. For some scientists, this makes the anthropic principle indispensable. For others, it makes it dangerous. But almost no careful discussion of fine-tuning can avoid it. In the end, the anthropic principle does not tell us that the universe was waiting for you. It tells us something quieter and more precise. Out of all the ways reality might have been, you could only awaken in one that allowed awakening at all. That does not make you the center of existence, but it does place you inside a rare kind of moment in a world ordered enough for matter to become awareness, and for awareness to look back across the dark. And perhaps there is something calming in that. The universe did not need to explain itself to the night, and yet somehow, through minds like yours, it softly began to try. Chapter 4: Inflation and the Birth of Bubble Universes. To understand why the multiverse became a serious scientific possibility, it is necessary to step back into the earliest moments of cosmic history and look at a theory that was never designed to sound poetic at all. Inflation began as an attempt to solve very technical problems in cosmology. It was proposed not to make the universe more mysterious, but to make it more intelligible. Yet once physicists followed the idea far enough, it began to suggest something astonishing: that our observable universe might be only one local region inside a much larger, inflating reality. The standard Big Bang model already explained a great deal. It described an expanding universe that had once been much hotter and denser. It gave a framework for understanding the cosmic microwave background, the relic radiation left over from the early universe, and it helped explain why the universe contains light elements in the proportions that observations broadly support. But as the model became more precise, certain puzzles stood out. One of them was the horizon problem. Distant regions of the universe appear to have nearly the same large-scale temperature and properties, even though in an ordinary expanding universe there may not have been enough time for those regions to exchange signals or come into thermal balance before the cosmic microwave background was released. Another was the flatness problem. Observations show that the large-scale geometry of the universe is very close to spatial flatness, and in the older picture, this required the early universe to begin in an extremely special state. Inflation was introduced as a way to address problems of this kind by proposing that, very early on, space itself underwent a brief era of extremely rapid, accelerated expansion. The beauty of inflation is that it changes the story of the early universe without discarding the larger Big Bang framework. It does not replace the hot early universe that later cooled into atoms, stars, and galaxies. Instead, it adds an earlier phase before the familiar hot expansion fully begins. In this picture, a very small region of space expands so dramatically that any initial curvature is stretched away, much as the surface of a very large sphere can look flat when viewed locally. Regions that were once close enough to share physical conditions are carried enormously far apart, which helps explain why the observable universe now looks so uniform on large scales. The result is that a universe which once seemed to require finely adjusted initial conditions can emerge from a dynamical process that drives it towards smoothness and near flatness. This is one reason inflation became so influential. It offered not merely a patch, but a mechanism. Inflation also does something even more important for modern cosmology. It provides a natural setting for the origin of the tiny primordial irregularities that later became galaxies and larger cosmic structures. In the inflationary picture, quantum fluctuations in the early universe can be stretched by the rapid expansion of space to enormous scales. Those fluctuations then become slight differences in density, leaving faint imprints in the cosmic microwave background and eventually guiding the growth of structure under gravity. In other words, inflation does not only smooth the universe, it also explains why the universe is not perfectly smooth. That balance is crucial. A cosmos with no irregularities would have remained too uniform to form galaxies, stars, or planets. A cosmos with too much irregularity could have become wildly inhomogeneous. Inflation offers a way to understand why the universe is smooth overall, while still containing the seeds of structure. Observations of the cosmic microwave background have been broadly consistent with this general picture, which is one of the main reasons inflation remains central to modern cosmology, even though many details are still debated. At this stage, inflation sounds like a bold but still fairly disciplined scientific idea. It helps explain the large-scale uniformity of the universe, its near-flat geometry, and the origin of the tiny fluctuations from which later structure grew. None of that yet requires a multiverse. The truly dramatic turn comes when physicists ask how inflation begins, how it ends, and whether it must end everywhere at once. In many simple mental pictures, one imagines inflation as a brief episode affecting the whole universe uniformly, after which ordinary cosmic evolution takes over. But some of the most studied models do not behave so neatly. Instead, they suggest that while inflation ends in some regions, it can continue in others. This possibility is known as eternal inflation. The phrase can sound misleading because it does not mean that every local region inflates forever in the same way. It means that inflation can continue globally even while ending locally. Certain parts of the larger space-time stop inflating, reheat, and evolve into regions like the one we inhabit, filled with matter, radiation, and the familiar long history of cosmic expansion. Other parts keep inflating, stretching faster than the non-inflating regions can consume them. The overall process never finishes everywhere. It keeps producing new post-inflationary regions again and again. In that setting, our observable universe would be one local pocket, or one bubble, inside a much larger structure. This is the point at which inflation stops being merely a theory of the early universe and becomes a generator of many universe-like domains. The word bubble is useful, but it can also be misleading if imagined too literally. These are not soap bubbles floating through empty space. They are regions in which the conditions of inflation have ended and a different phase of cosmic evolution has begun. Inside such a region, space can expand more slowly, particles can form, radiation can fill the cosmos, and the long story leading to stars and galaxies can unfold. Outside it, inflation may still continue. Because the surrounding space is expanding so rapidly, these bubble regions can become effectively isolated from one another. Even if the larger reality contains countless such regions, they need not be able to communicate in any practical way. Each would appear, from the inside, like an enormous universe in its own right. That is why eternal inflation became one of the most influential scientific routes to a multiverse. It does not begin with a desire to imagine parallel worlds. It begins with the internal logic of inflationary dynamics. There is also a deeper reason bubble universes became especially interesting. If different pockets can emerge from different vacuum states or different local physical conditions, then they may not all share exactly the same large-scale properties. Some may have different effective constants, different symmetry breakings, or different histories of structure formation. This possibility later became especially important when eternal inflation was discussed alongside string theory landscapes, where many possible vacuum configurations might exist. Inflation, in that broader setting, becomes not only a way to make many regions, but a way to populate many kinds of regions. That connection helped transform the multiverse from a loose philosophical speculation into something tied to active theoretical physics. Still, scientific caution matters here. Inflation itself is much more established as a research framework than eternal inflation is as a confirmed description of reality. The broad inflationary idea is taken seriously because it helps account for several observed features of the universe, and because its predictions about primordial fluctuations have been empirically fruitful. Eternal inflation, by contrast, is a more speculative extension of some inflationary models. It is not directly observed. No one has seen another bubble universe. No telescope has photographed a neighboring cosmic domain. The argument is theoretical. If inflation works in certain ways, then a larger self-reproducing structure can follow. This distinction is essential for honesty. One can say that inflation is a major part of modern cosmology, while also admitting that the bubble universe picture remains hypothetical. There are additional complications. Eternal inflation creates difficult problems about probability and prediction. If infinitely many bubble universes are produced, how should one define what is typical? How does one compare different kinds of regions in a mathematically meaningful way? These questions are part of what cosmologists call the measure problem. It is not a minor technical nuisance. It goes to the heart of whether eternal inflation can generate clean predictions or only a vast set of possibilities. This is one reason why the multiverse remains controversial even among physicists who take inflation very seriously. A theory that produces everything too easily can risk explaining too little, unless it also tells us how to assign probabilities and expectations in a disciplined way. And yet the idea remains compelling because it emerges from such a natural line of reasoning. A theory introduced to explain the smoothness and geometry of our early universe seems, in some versions, unable to stop at only one universe-like region. It spills outward, it keeps going. What began as a solution to technical cosmological puzzles becomes a picture in which our cosmic home is only one finished patch in a much larger unfinished process. That is what makes inflation such a powerful chapter in the story of the multiverse. It shows how a sober scientific theory can, when followed carefully, lead to a vision of reality that feels almost mythic in scale. Perhaps that is part of what makes this chapter so quietly moving. The stars above you may already feel immense, but inflation suggests that even our entire visible cosmos could be local, not ultimate. What seems endless to us may be only one calm interior region in a reality still unfolding beyond all sight. And there is something strangely peaceful in that thought. Your life is small beneath the sky, but the sky itself may be small beneath existence. And somehow, in one warm corner of one possible bubble, you are here to wonder. Chapter 5: Quantum Mechanics and the Many Worlds Idea. Quantum mechanics is one of the most successful scientific theories ever created. Yet it describes reality in a way that still feels almost deliberately resistant to ordinary human intuition. It explains the behavior of atoms, electrons, light, and countless experiments with extraordinary accuracy. But when physicists try to describe what the theory says reality is actually doing, deep disagreements appear. This is where the many worlds idea enters the story. It was not invented because scientists wanted to turn physics into fantasy. It emerged from an attempt to take the mathematical structure of quantum mechanics seriously, even when that structure points toward conclusions that seem profoundly strange. To understand why, it helps to begin with one of the central features of quantum theory: superposition. In classical physics, a system is expected to have definite properties whether or not we look at it. A planet has a position and velocity. A ball is either here or there. But in quantum mechanics, a system can be described by a state that combines multiple possible outcomes at once. This does not mean that particles are simply confused little objects hiding a secret classical state from us. The formalism treats the superposed state as the basic physical description used to predict interference effects and measurement statistics. Quantum theory works precisely because these superposed states are real parts of the theory, not just bookkeeping tricks. Modern experiments involving controlled quantum states, including the kinds highlighted in Nobel discussions of superposition and entanglement, depend on that fact. The difficulty comes when a measurement seems to produce only one result. Before a measurement, quantum theory may assign several possible outcomes with different amplitudes. After a measurement, an observer sees one definite result. In the traditional textbook language, the state is said to collapse, but this creates a conceptual problem. The ordinary time evolution of quantum mechanics is smooth and deterministic. Collapse, by contrast, looks sudden, special, and unlike the rest of the theory. Why should observation introduce a fundamentally different kind of physical process? What exactly counts as a measurement? And where does the boundary lie between the quantum world and the classical world of definite outcomes? These questions form part of what physicists call the measurement problem. The many-worlds interpretation is one attempt to answer it by refusing to add collapse at all. This approach is associated most famously with Hugh Everett. Everett proposed that one could keep only the ordinary quantum evolution and drop the extra collapse rule. In that picture, the universal quantum state evolves continuously according to the same mathematical law at all times. Measurement is not a magical interruption of physics. It is a physical interaction like any other, one that entangles the observer with the system being observed. Instead of a single result being selected by collapse, the combined system evolves into a state in which different possible outcomes are correlated with different observer states. In simple language, different branches of reality emerge, each containing an observer who experiences one outcome as definite. The world does not choose one path and erase the others. The total state continues to include them all. That is why the many worlds interpretation can sound so startling. It suggests that the apparent uniqueness of a measurement result may be local rather than absolute. From inside one branch, you experience one definite history. You never feel yourself spread across incompatible outcomes. You simply see one detector click, one path taken, one record written. Yet according to the interpretation, other branches continue as well, containing other consistent records of different outcomes. These are not imagined possibilities in the usual sense. They are supposed to be physically real components of the total quantum description. What we call a world is then not the whole of reality, but one effectively separate branch within a larger quantum state. A crucial concept here is decoherence. Without it, many worlds would sound too vague, because one would want to know why we do not constantly experience bizarre mixtures of incompatible outcomes. Decoherence describes what happens when a quantum system interacts with its environment. In principle, quantum states can interfere with one another, but in practice, Once a system becomes entangled with a vast environment, the delicate phase relations needed for observable interference between different components become effectively inaccessible. The result is that certain branches become dynamically stable and stop behaving like one blended superposition from the perspective of local observers. Decoherence does not literally destroy parts of the wave function, and by itself, it does not solve every philosophical issue. But it explains why the world looks classical in practice, and why distinct measurement records can emerge without adding a special collapse law. This point is essential because many worlds is often misunderstood as a dramatic claim that every tiny event creates a cartoon explosion of universes. The scientific version is more restrained and more technical. It says that the universal quantum state evolves continuously, and that what we call worlds are stable, effectively non-interfering structures within that evolving state. The boundaries of a branch are not always sharp in the everyday sense, and not every microscopic interaction should be spoken of in simple, popular language as a separate, fully formed universe. Even supporters of Everettian ideas often emphasize that worlds are emergent structures, not extra little planets stacked in hidden space. They arise from the branching structure associated with decoherence and measurement-like interactions. So why do different versions of an observer seem to make different decisions in this picture? The careful answer is that the branching is tied first to different physical outcomes. Once branches have separated and no longer effectively interfere, the observer in each branch continues forward with a different record of what happened. From that point on, those observer copies are no longer in exactly the same situation. They have different memories, different evidence, and sometimes different surroundings. Later choices can then diverge because the histories have diverged. The interpretation does not require mystical free will jumping between worlds. It only requires that when reality develops into different decohered branches, each branch contains its own continuation of the observer, and those continuations then live through different unfolding circumstances. Supporters of many worlds are drawn to the interpretation for several reasons. One is conceptual economy. Instead of using one law for ordinary quantum evolution and another for collapse, they keep only one basic dynamical rule. Another is that many worlds avoids faster-than-light collapse effects as fundamental features of nature, since all outcomes remain in the total quantum state. It also treats observers as physical systems inside the theory rather than exceptions standing partly outside it. In that sense, the interpretation is radical, but also deeply conservative. It does not add extra dynamical machinery. It removes a special rule and accepts the consequences. Some philosophers and physicists find that attractive precisely because it makes quantum theory more uniform. Still, many worlds is not universally accepted, and the objections are serious. One famous issue concerns probability. If all outcomes occur, what does it mean to say one outcome is probable and another is not? In ordinary experiments, quantum theory gives precise probabilities for results. Everettian interpretations must explain why rational observers inside branches should use the standard quantum probabilities, even though at the level of the whole state, every allowed outcome still exists. A great deal of technical and philosophical work has been devoted to this question, and different Everettian approaches answer it in different ways, often using ideas about typicality, decision theory, or branch weights. But the issue remains one of the main reasons the interpretation is debated. Another issue is ontological clarity. Critics ask what exactly counts as a world, how branching should be defined precisely, and whether the interpretation really explains definite experience or merely redescribes it. Decoherence helps identify stable branch-like structures, but some philosophers argue that this still leaves open questions about the exact status of multiplicity. Others object that many worlds seems extravagant because it retains every possible outcome rather than selecting one. Supporters respond that extravagance in worlds may be the price of simplicity in laws. From their point of view, it is collapse theories that add awkward extra rules, while many worlds simply accepts the mathematics of quantum theory at face value. This disagreement has not been resolved, which is why many worlds remains an interpretation rather than an established empirical fact. It is also important to say what many worlds does not claim. It does not mean that every imaginable fantasy is realized somewhere. Branching is constrained by the actual structure of the quantum state and the laws of physics. It does not permit logical contradictions, and it does not turn science into unrestricted storytelling. Nor does it mean that other branches are easily accessible or that one can communicate with alternate versions of oneself. Decoherence is powerful precisely because it makes branches effectively autonomous for practical purposes. The interpretation, if true, would enlarge reality dramatically, but it would not grant everyday access to that enlarged structure. Other branches would be real in the theory while remaining inaccessible in ordinary experience. What makes the many worlds idea so important for the multiverse story is that it introduces a very different route to multiplicity than inflationary cosmology. In the inflationary picture, many universe-like regions arise through cosmic dynamics on enormous scales. In the Everettian picture, multiplicity arises from the interpretation of quantum mechanics itself. The many are not mainly remote bubbles beyond a cosmic horizon, but branches of one quantum reality. These two ideas are conceptually distinct, though both are often grouped under the broad label of multiverse. That difference matters because it shows that the multiverse is not one single hypothesis. It is a family of possibilities born from different scientific pressures. In the case of many worlds, the pressure comes from the desire to understand measurement without collapse. Perhaps that is why the idea stays with people long after they first hear it. Quantum mechanics already teaches that reality is not built in the image of common sense. Many worlds pushes that lesson further and asks whether the single life you experience is only one thread through a larger fabric of outcomes. Science has not proven that this picture is true, and careful physicists still disagree deeply about it. But even as a possibility, it carries a strange kind of quiet weight. It suggests that reality may be far more abundant than perception reveals, and that what feels final from within one moment may be only local in a deeper structure. And as the day loosens and your thoughts begin to soften, there is something oddly peaceful in that. You do not need to hold the whole fabric in your mind. It is enough to rest inside one branch of it, here and now, while the wider mystery remains gently beyond reach. Chapter 6: String Theory, Extra Dimensions, and the Cosmic Landscape. String theory entered physics as an attempt to answer one of the deepest problems in fundamental science: how to describe gravity and quantum mechanics within a single consistent framework. In ordinary quantum field theory, the basic ingredients are point-like particles. In string theory, those point-like entities are replaced by extremely tiny one-dimensional objects called strings, and different vibrational patterns of those strings correspond to different kinds of particles. What made the idea especially attractive to many theorists is that a quantum description of a vibrating string naturally includes a particle with the right properties to behave like a graviton, the hypothetical quantum carrier of gravity. That meant string theory was not only another particle model. It looked, at least in principle, like a route toward quantum gravity. But the theory came with a price. It did not fit comfortably inside the familiar picture of a universe with only the 3 dimensions of space and 1 dimension of time that we directly experience. In the best-known superstring formulations, mathematical consistency requires extra spatial dimensions beyond the visible ones. NASA's educational summary of superstrings describes this as a world in which some dimensions are large enough for us to perceive, while others are curled up on scales too small to notice directly. This is one of the most famous features of string theory, and one of the easiest to misunderstand. Extra dimensions are not usually imagined as hidden rooms folded somewhere behind the sky. They are additional directions built into the fundamental geometry of the theory, but compactified so tightly that ordinary motion through daily life does not reveal them. The idea of compactification is essential here. If extra dimensions exist, the reason we do not see them in ordinary experience may be that they are wrapped up into extremely small geometric shapes. A useful analogy, though only an analogy, is to imagine a very long hose viewed from far away. At a great distance, it may look like a one-dimensional line, even though close inspection reveals a second circular direction around its surface. In string theory, the unseen dimensions are not necessarily simple circles, and in many models they are far more intricate than that. Their shape matters because strings vibrating through a particular compact geometry can produce one pattern of particles and interactions rather than another. The hidden shape of the extra dimensions therefore helps determine the effective physics of the larger world we observe. That feature is what makes string theories so important for multiverse discussions. At first glance, one might imagine there should be a single correct way to compactify the extra dimensions, leading to one unique low-energy universe. But the theory did not settle so neatly. Over time, string theorists found that there appear to be a vast number of possible vacuum states, sometimes called vacua, corresponding to different stable or metastable ways of arranging the extra dimensions, fluxes, and associated fields. At the level of observable physics, different vacua can correspond to different effective constants, particle spectra, and symmetry structures. The Stanford Encyclopedia of Philosophy notes this directly in its discussion of fine-tuning, explaining that string theory appears to contain an enormous number of lowest energy states that would manifest at higher levels as different physical laws or constants. This is the basic idea behind what became known as the string landscape. The word landscape is helpful because it suggests a theory with not one inevitable resting place but many possible valleys. If a fundamental theory allows a huge number of locally stable configurations, then what we call our universe may reflect only one such configuration rather than the uniquely necessary form of reality. In this picture, the laws we observe are not necessarily the only logically or physically possible laws. They may be environmental features tied to the vacuum state realized in our own cosmic region. That is a major conceptual shift. Instead of expecting a final theory to dictate a single universe with no alternatives, one begins to consider the possibility that the deepest theory permits many realizations, and that the universe we inhabit is one local expression among many. By itself, however, a landscape of possible vacua does not yet produce a multiverse. It gives a menu of possibilities, but not necessarily a mechanism for realizing them. This is where string theory became closely linked to eternal inflation. In inflationary cosmology, as discussed in the previous chapter, some models suggest that inflation can continue globally even while ending locally in separate bubble-like regions. When that inflationary picture is combined with a landscape containing many possible vacuum states, one obtains a striking scenario. Different bubble universes may settle into different locations within the landscape. In other words, inflation can play the role of populating the landscape. One region may cool into one effective set of laws, while another settles into a different one. Britannica's treatment of multiverse theories notes precisely this synergy between eternal inflation and the string landscape. This matters because it offers a new way to think about fine-tuning. Earlier, the puzzle was why the constants and conditions of our universe seemed so unusually compatible with long-lived structure and life. In a landscape multiverse, that question changes form. The deep theory may allow many possible low-energy worlds, most of which are uninhabitable or radically different from our own. Observers would then naturally arise only in the comparatively rare domains where the conditions permit complex structure. The explanation is no longer that the fundamental theory singled out our universe as uniquely special. Instead, the theory may generate a huge range of possibilities, and we find ourselves in one of the hospitable regions simply because inhospitable regions contain no one to notice them. This is one of the strongest reasons string theory became relevant to multiverse reasoning, rather than remaining only a technical attempt at unification. At the same time, scientific caution is especially important here. String theory is mathematically rich and intellectually influential, but it is not an experimentally confirmed description of nature. No laboratory has directly detected a fundamental string. No experiment has directly revealed the compact extra dimensions posited by the theory. CERN discussions of extra dimensions explain that models with extra dimensions can imply experimental signatures, such as heavier recurrences of particles, but the existence of extra dimensions has not been established by current evidence. That means the landscape is even more speculative still, because it depends not only on string theory being broadly right, but also on a particular picture of its vacuum structure, and on cosmological mechanisms that realize multiple vacuum states in actual regions of reality. A careful script has to preserve that hierarchy of certainty. String theory is a major theoretical framework. Extra dimensions are part of many of its formulations. The landscape is a further theoretical development. The multiverse interpretation built from it is more speculative again. There's also a conceptual challenge hiding beneath the excitement. For many physicists, the hope of a fundamental theory was that it would explain why the universe has the laws it has and could not have been otherwise. The landscape seems to move in the opposite direction. It suggests that the deeper theory might permit an enormous variety of possible worlds. To some researchers, that feels like progress because it connects naturally with inflation and anthropic reasoning and may help explain why our observable laws appear contingent. To others, it feels disappointing because it weakens the dream of a uniquely determined cosmos. If the final theory allows too many possibilities, one may worry that it stops predicting enough. This tension is one reason the landscape remains controversial. It is not merely a technical issue. It changes what many physicists mean when they ask for an explanation of the laws of nature. Even the phrase extra dimensions can create the wrong emotional picture if handled carelessly. These dimensions are not added for decoration. In string theory, they arise from mathematical consistency conditions and from the requirement that the theory behave in certain stable ways. They also do not automatically imply that other universes are stacked nearby like pages in a book. Some models in string theory-inspired cosmology do use brains and higher dimensional structures in ways that invite that imagery, and NASA has public visualizations that illustrate brain world concepts, but such pictures should not be confused with established reality. The safest scientific description is more restrained. String theory permits a richer underlying geometry than the visible world reveals, and in some theoretical developments, that richer geometry allows many distinct effective universes. Perhaps the deepest significance of the cosmic landscape is philosophical as much as physical. It challenges the instinct that the visible laws of our universe must be the only possible final arrangement. It suggests that what we call the laws of nature may partly reflect where reality settled, not merely what reality is in its deepest essence. That possibility is still unproven, and many physicists remain skeptical for good reason. Yet the idea continues to shape serious discussions because it grows out of an ambitious attempt to unify the foundations of physics rather than from pure speculation alone. It is one more place where the pursuit of mathematical consistency unexpectedly opens the door to a reality larger than the one we directly inhabit. And there is something quietly humbling in that thought. The world that feels complete around you may be only one settled pattern among countless possible patterns hidden in a deeper structure. The laws that seem eternal to us may be local, like the climate of one valley in a landscape too vast to cross. Yet in this one valley, among these stars and atoms and brief human thoughts, consciousness still arose and wondered what kind of place had allowed it. And as the night grows softer, that may be enough. You do not need to see the whole landscape to rest within one of its quiet clearings. Chapter 7. Could other universes have different laws of physics? By the time the multiverse idea reaches this stage, the question becomes even more unsettling than the existence of many universes itself. It is one thing to imagine that there may be other cosmic regions beyond our own. It is another to ask whether those regions might not only look different, but actually run on different physical rules. Could gravity have a different strength elsewhere? Could atoms behave differently? Could stars fail to ignite, or chemistry fail to become rich enough for complexity? Could there be universes in which the very structure of matter, space, or time departs so far from our own that nothing familiar could exist there at all? This possibility is one of the main reasons the multiverse feels both scientifically serious and emotionally strange. It shifts the question from where other universes might be to what kind of realities they might contain. To approach that carefully, it helps to clarify what physicists mean by the laws of physics. In one sense, the laws are the deep regularities and mathematical structures that describe how nature behaves. In another sense, what we casually call the laws may include several distinct things: the basic dynamical framework, the types of particles that exist, the strengths of the fundamental interactions, the values of constants, the number of large dimensions, and the vacuum state in which low-energy physics plays out. These are not all the same kind of ingredient. The universe could, in principle, share the same deepest theory as ours, while still displaying different effective physics because it realizes different constants or different symmetry breaking. So when people speak about other universes with different laws, they do not always mean a total abandonment of all common structure. Sometimes they mean something subtler. The same underlying framework may allow different low-energy worlds. This distinction matters because it keeps the discussion scientific rather than purely imaginative. Modern particle physics already teaches that the visible world depends not only on abstract equations, but also on how symmetries are realized and how fields settle into particular states. CERN's overview of the Standard Model emphasizes that the world we observe is built from a specific set of particles and force carriers. If a different universe contained a different effective particle spectrum, or if the strengths of interactions differed significantly, the resultant cosmic history could be transformed. Matter might not clump in the same way. Stable atoms might not exist in familiar form. Nuclear processes inside stars might never produce the range of elements that makes planets and chemistry possible here. This is why the question is scientifically meaningful. Small shifts in foundational ingredients can have large consequences for the emergence of structure. One obvious place to begin is with the constants of nature. In our universe, the behavior of matter depends on quantities such as the relative strengths of the electromagnetic, strong, weak, and gravitational interactions, along with the masses and charges of basic particles. Fine-tuning discussions in philosophy of physics and cosmology ask whether a universe even slightly different in some of these respects would remain life-permitting or structurally rich. The point is not that physicists have explored every conceivable alternative cosmos in full detail. The point is that many pathways to complexity appear sensitive to these values. Change them enough, and stars might burn too differently, nuclei might become unstable, or chemistry might lose the balance needed for complex molecules. In that sense, other universes with different constants could still be genuine universes, but they might be dark, simple, short-lived, or radically alien compared with ours. Even so, there is an important caution. We do not know that the constants are truly free to vary independently. A deeper theory may link them together. What now looks like a menu of separate adjustable quantities may later turn out to be the consequence of one deeper structure. This means that when scientists imagine alternative universes, they often perform controlled thought experiments rather than claim a complete survey of all real possibilities. They ask what would happen if one feature changed while others remained roughly the same, not because nature must allow exactly that change in isolation, but because it helps reveal how sensitive familiar structure is to underlying conditions. So the question of different laws is partly physical and partly methodological. It is a way of probing which aspects of our universe are robust and which are contingent. Another route to different laws comes from the idea of vacuum states. In quantum field theory, and especially in string-inspired cosmology, empty space is not truly featureless. The vacuum can carry structure. Different vacuum states can correspond to different low-energy properties, different symmetries, or different effective constants. This is one reason the string landscape became so central to multiverse reasoning. If the deeper theory allows many possible vacuum configurations, then different cosmic regions may cool into different effective worlds. In that picture, the laws observed locally are not simply the only possible laws. They are the laws associated with one realized vacuum among many. The Stanford Encyclopedia of Philosophy notes this ability directly when discussing fine-tuning and the string landscape. Different lowest energy states could manifest as different effective laws or constants at higher levels. If that is right, then different laws may not mean total disorder. They may mean different local realizations of a broader theory. One universe might still have forces and particles, but not the same ones in the same arrangement. Another might have stable matter, but no chemistry resembling ours. Another might expand so quickly that galaxies never form. Another might collapse too soon for long cosmic history to develop. The difference between such universes would not necessarily be like the difference between science and fantasy. It would be more like the difference between one physical environment and another, except magnified to the level of an entire cosmos. The possibility of different dimensions deepens the issue further. In string theory, extra dimensions arise from the mathematical consistency of the framework, and the way those dimensions are compactified helps determine observable physics. Change the geometry of the compact dimensions, and the resulting world can change as well. It is therefore possible, at least within that theoretical setting, that different universes could have not only different constants but different geometric foundations that shape their particles and interactions. Some universes might still contain 3 large spatial dimensions like ours. Others, depending on the model, might not produce a low-energy world remotely similar to ours at all. This is one reason dimensionality is often discussed alongside habitability. The kind of stable orbital and structural behavior familiar in our universe may rely in part on the dimensional structure we actually have. That does not prove other dimensional arrangements are impossible. It does suggest they may give rise to very different kinds of order, if any. Yet the phrase different laws of physics can easily tempt the imagination too far. Science does not currently provide a catalog of alternate universes with certified rulebooks. No observation has directly shown us a neighboring cosmos where gravity behaves differently. These possibilities arise from extrapolating serious theoretical frameworks, not from direct measurement of other worlds. That is why careful physicists distinguish between what is observed and what is inferred. We observe one universe with one set of effective laws. The idea that other universes could differ comes from theories that permit multiple realizations, such as eternal inflation combined with a landscape of vacua, or from fine-tuning arguments that suggest many alternative parameter choices would lead to different outcomes. The hypothesis is meaningful, but it remains speculative. There is also a subtle philosophical question hiding inside all of this. How different can a universe be before it stops counting as a universe in any intelligible sense? If there are no stable structures, no enduring patterns, and no possibility of complex organization, then such a reality may still exist physically, while being almost impossible for minds like ours to imagine from within. Much of the multiverse discussion therefore focuses not on all logically imaginable worlds, but on worlds generated by respectable physical theories. That keeps the subject anchored. Scientists are not usually asking whether absolutely anything can exist somewhere. They are asking whether our best theories imply many realized domains, and whether those domains may differ in systematic ways. This is why the question matters so much for the multiverse as a whole. If every universe had exactly the same laws and constants as ours, then multiplicity would still be grand, but it would not explain much about fine-tuning or cosmic contingency. The real explanatory power of the multiverse appears only when diversity enters the picture. If there are many universes, and if they differ, then our own universe may be one habitable outcome among a wider spread of possibilities. In that case, the apparent specialness of our world might reflect selection rather than uniqueness. We would observe this kind of universe because only this kind, or something close to it, allows observers to emerge. That does not prove the multiverse is true, but it shows why the question of different laws is not decorative. It sits near the center of the entire argument. At the same time, this possibility changes the emotional tone of cosmology. It suggests that what we call the laws of nature may not be universally inevitable. They may be local facts about our region of reality, like the climate of one valley rather than the shape of all existence. The equations that feel absolute to us may be provincial in a deeper landscape. That is a difficult thought because science has often advanced by seeking universality, but it is also a strangely beautiful one. It means that reality may be richer than one pattern, broader than one way for matter to exist, and more inventive than one cosmic script. And if that is true, then the quiet order around you tonight may be more precious than it first appears. In this universe, atoms hold, stars shine long enough to seed the dark with heavier elements, and minds can wake inside matter and ask why there is something rather than nothing. Perhaps elsewhere the laws are different, and the story never reaches this point. But here it did. Here, in one lawful corner of reality, the universe became calm enough to know itself for a while. And as your thoughts begin to slow, you can let that be enough. Not certainty, not final answers. Only the gentle fact that among whatever other possibilities may exist, you arrived in one where wonder was possible. Chapter 8. Can the multiverse ever be tested? At this point in the story, the multiverse faces its hardest question, not whether it is fascinating, not whether it grows naturally out of some important ideas in cosmology and quantum theory, but whether it belongs to science in the strongest sense at all. A theory may be bold, elegant, and mathematically suggestive, yet still fail if it cannot connect to observation in a meaningful way. So when scientists ask whether the multiverse can ever be tested, they are not asking a small technical question. They are asking whether this grand idea can cross the difficult boundary between speculation and evidence. That boundary is not always as sharp as people imagine. In science, not everything must be directly seen in order to count as real. No one has ever looked at a quark with the naked eye, yet particle physics is full of well-supported entities inferred from converging evidence. Black holes were accepted long before we had direct imaging of one, because theory and observation pointed together in the same direction. Science often works by testing consequences rather than touching the thing itself. So the real issue is not whether another universe can be visited or photographed. The issue is whether theories that imply a multiverse also make observable predictions, or at least distinctive indirect commitments that can be checked against data. That is the strongest case multiverse supporters can make, and it is also where the criticisms become sharpest. In the inflationary version of the multiverse, the most discussed testing strategy comes from cosmic bubble collisions. If our observable universe formed as one bubble within a larger eternally inflating background, and if other bubbles formed nearby, then in principle collisions between such regions could have left faint imprints in the cosmic microwave background. This is one of the few cases in which a multiverse model seems to offer a possible observational trace rather than pure metaphysical distance. Researchers have searched microwave background data for such patterns, including studies explicitly framed as observational tests of eternal inflation. Those searches are scientifically important even when they do not find evidence, because they show that some multiverse ideas are not completely detached from empirical reasoning. At the same time, no accepted observation has yet confirmed a bubble collision, and the expected signatures are model-dependent and difficult to distinguish from statistical noise or other astrophysical effects. So this line of work is promising in principle but still inconclusive in practice. A second route to testability is more indirect. Instead of looking for another universe itself, scientists ask whether the parent theory that gives rise to a multiverse is independently supported. Inflation is the clearest example. Inflationary cosmology was not proposed to create a multiverse. It was introduced to explain features of the early universe, such as its large-scale smoothness, near-flat spatial geometry, and the primordial fluctuations that later seeded galaxies. Many observations are broadly consistent with this inflationary framework, but support for inflation is not the same as proof of eternal inflation. And proof of eternal inflation would still not automatically confirm every multiverse claim built on top of it. This layered structure matters. One can reasonably say that some observational successes make the broader theoretical pathway to a multiverse more serious, while also admitting that the more extravagant consequences remain unverified. This is exactly why the multiverse debate is so persistent. The supporting structure is neither empty nor decisive. The same problem appears in string theory and the cosmic landscape. A landscape picture can suggest many possible low-energy worlds, and inflation can supply a mechanism for populating them. But to turn that into testable science, one would need more than the existence of a vast menu of possibilities. One would need a principled way to connect that menu to concrete expectations about the universe we observe. This is where the multiverse runs into one of its deepest technical obstacles, known as the measure problem. In many eternal inflation scenarios, the total number of bubble universes can become effectively unbounded. If everything allowed by the theory happens over and over, the ordinary notion of probability becomes difficult to define. Without a well-motivated measure, it becomes unclear how to say what should be typical, rare, expected, or surprising. And without that, even a rich theory can struggle to produce sharp predictions. This is not a minor philosophical complaint from outside science. It is an internal problem about how to extract observational meaning from the framework itself. That difficulty is one reason some physicists argue that the multiverse remains scientifically incomplete rather than outright unscientific. They do not necessarily reject it because it reaches beyond direct observation. They worry that it has not yet matured into a predictive framework with enough constraint. A theory that allows too many outcomes too easily can lose explanatory force. If almost any observed universe can be accommodated somewhere in the ensemble, then the theory risks becoming flexible in the wrong way. This concern becomes especially sharp when anthropic reasoning enters the picture. Anthropic arguments can sometimes help explain why observers should not be surprised to find themselves in a life-permitting universe. But if used carelessly, they can also reduce explanation to a kind of after-the-fact acceptance. The universe is this way because otherwise we would not be here. That may be partly true, but many scientists do not want it to become the end of the conversation. They want deeper physical reasons whenever possible. The many worlds version of the multiverse faces a different testing problem. In that picture, the challenge is not looking for another cosmic bubble beyond the horizon. It is deciding whether the branching structure of quantum mechanics can be distinguished empirically from rival interpretations. The many worlds idea takes the formalism of quantum theory seriously and avoids a special collapse rule, while decoherence explains why branches behave like effectively separate classical histories. But here the crucial issue is that many interpretations of quantum mechanics often agree on the observed experimental results. They differ in ontology, in what they say the mathematics means, rather than in the measurement statistics themselves. That makes direct empirical adjudication difficult. If two interpretations make the same laboratory predictions, the contest between them may be guided as much by conceptual virtues such as simplicity, coherence, and explanatory scope as by new data. That does not make the debate meaningless, but it does mean that the many worlds multiverse is hard to test in the straightforward experimental sense people often expect. This brings us to a more general philosophical point. Testability is not a single yes or no switch. Some theories are directly testable now. Some are indirectly testable through consequences of a broader framework. Some are testable in principle, but not yet in practice, because our instruments are limited. Others are so weakly connected to observation that they risk slipping beyond science. The multiverse may occupy different positions on that spectrum, depending on which version one is talking about. A bubble collision scenario in eternal inflation is not in the same epistemic position as a vague claim that anything imaginable exists somewhere. An Everettian interpretation of quantum mechanics is not in the same position as a speculative popular narrative about parallel selves making every possible choice. Part of the confusion around the multiverse comes from treating all versions as though they rise or fall together. They do not. Some are tied to serious research programs with at least partial observational hooks. Others remain much looser. Even the absence of evidence can matter, though in a limited way. If scientists keep looking for bubble collision signatures and find none, that can constrain certain models of eternal inflation. If cosmological observations continue to favor inflation in some forms while disfavoring others, that can narrow the space of multiverse-generating theories. If particle physics and cosmology fail to support the kinds of mechanisms needed for a landscape picture, that weakens the case. Science often progresses not by dramatic confirmation alone, but by pruning possibilities. The multiverse may be approached in the same way, through a gradual narrowing of viable theoretical pathways, rather than through one spectacular photograph of another universe. Still, many critics remain unconvinced, and their caution is reasonable. They argue that if another universe is permanently unobservable, then invoking it may explain too much too cheaply. They worry that the multiverse can become a refuge for theories that would otherwise face sharper demands for uniqueness and prediction. They point out that a successful scientific explanation should ideally tell us not only that our universe is allowed, but why it should have been expected. These criticisms do not prove the multiverse is false, but they do explain why the debate is alive and serious. The strongest defenders of the multiverse know that testability is the central issue, and the strongest critics know that some multiverse ideas are more disciplined than casual dismissals admit. So can the multiverse ever be tested? The most honest answer is not a clean yes and not a clean no. Some versions may leave indirect traces, constrainable signatures, or empirical commitments through the broader theories that produce them. Other versions may remain interpretive frameworks rather than experimentally distinct theories, and some may never rise above speculative possibility. The multiverse is therefore not one scientific object with one evidential status. It is a family of ideas, each with its own relationship to observation. That is less tidy than people often want, but it is also the truth. Science sometimes advances through clear detection, and sometimes through a longer struggle over what counts as evidence in the first place. There is something quietly fitting about that. A reality large enough to contain many universes may not reveal itself in simple dramatic ways. It may first appear only as pressure at the edge of theory, as a question that our best equations refuse to let go of. Perhaps that is frustrating. Perhaps it is also beautiful. The universe has already given us enough mystery to fill a lifetime, and still it may be only one local answer among many. Tonight, you do not need to settle that question. It is enough to feel how far the human mind has reached into the dark and how softly it continues, still asking what else may be there. Chapter 9. The Problems, Debates, and Criticisms of the Multiverse. By this point, the multiverse can seem almost irresistible. It appears at the edge of inflationary cosmology, it appears in some readings of quantum mechanics, and it becomes especially tempting when physicists try to make sense of fine-tuning. But this is exactly where the deepest criticisms begin. The multiverse is not challenged because it is too imaginative. It is challenged because science demands more than imagination, more than elegance, and more than a theory's ability to sound profound. It demands clarity about evidence, prediction, and explanation. The multiverse remains controversial because many scientists believe it may eventually answer real questions, while many others worry that it risks weakening the standards by which scientific answers are judged. The most familiar criticism is untestability. If other universes are permanently beyond observation, then how can their existence count as part of empirical science rather than speculative metaphysics? This is not a superficial complaint. In ordinary scientific practice, even entities that cannot be directly seen are accepted because they leave robust, checkable effects within the observable world. Critics argue that many versions of the multiverse do not yet meet that standard. They worry that the multiverse can become a kind of explanatory shelter, a place where a theory escapes falsification by placing its most important consequences forever outside observational reach. Supporters answer that some multiverse proposals are connected to broader theories that do make testable predictions, and that indirect support may still matter. But even many sympathetic philosophers of cosmology agree that testability is the central pressure point in the whole discussion. A second criticism concerns predictability. A good scientific theory does not merely allow the world we observe. It should also make that world more expectable than rival possibilities, or at least constrain what sorts of worlds are likely. The problem is that some multiverse frameworks seem too permissive. If they generate a vast or even effectively unlimited range of universes, then almost any observation might be compatible with the theory somewhere. In that case, the theory risks explaining everything and therefore nothing. This concern is especially sharp in eternal inflation and in landscape-style reasoning, where one often needs additional assumptions to say what counts as typical or probable. Without those assumptions, the multiverse can look less like a predictive theory and more like an enormous catalog in which every result eventually appears. That problem leads directly into one of the most technical and most serious criticisms, the measure problem. In many multiverse models, especially those involving eternal inflation, the total number of universe-like regions can become unbounded. If there are endlessly many domains of different kinds, how should probabilities be assigned? What does it even mean to say that one kind of universe is more common than another if both occur infinitely often? Different ways of regulating or counting the ensemble can lead to different answers, and sometimes radically different answers. That is deeply troubling because the predictive content of the theory may depend on the chosen measure. The issue is not merely that the mathematics is hard. It is that the theory may not yet tell us, in a unique and principled way, how to extract observational expectations from its own structure. Many critics see this as one of the strongest reasons to remain cautious about the multiverse. Closely related to this is the problem of typicality. Even if one could define a measure, one still has to ask whether observers like us should count as typical observers in the relevant ensemble. This may sound harmless, but it quickly becomes strange. In a sufficiently large multiverse, bizarre observers produced by rare fluctuations may outnumber ordinary observers who arise through long cosmic history. If so, then a naive typicality assumption can lead to absurd conclusions about what we should expect to see. This family of worries appears in discussions of so-called Boltzmann brains, hypothetical self-aware entities that fluctuate into existence with misleading memories rather than evolving inside stable planetary environments. If a theory predicts that such observers dominate, then the fact that we seem to inhabit an orderly external world becomes evidence against the theory, or at least against how its probabilities are being handled. These problems show that the multiverse debate is not only about imagination. It is also about very sharp internal standards of consistency. Another major debate concerns anthropic reasoning. The anthropic principle, used carefully, reminds us that observers can only find themselves in observer-permitting conditions. That insight is legitimate and often important. But critics worry that multiverse arguments rely on it too heavily. If every puzzling feature of our universe is answered by saying that otherwise we would not be here, then explanation can start to feel too easy. Rather than discovering why the laws have the form they do, one simply says that all forms occur somewhere, and we naturally occupy one of the habitable cases. For some scientists, that move is reasonable when a deeper dynamical explanation is unavailable. For others, it feels like surrender, as though physics were giving up on the older hope of finding necessity beneath apparent contingency. The criticism is not that anthropic reasoning is always wrong. It is that it may be too weak to bear the full weight of explanation on its own. There's also a disagreement about what science should aim for at the deepest level. Traditionally, many physicists hoped that a final theory would uniquely determine the basic structure of reality. On that view, the ultimate laws would not merely permit our universe, they would single it out. The multiverse changes that aspiration. It suggests that the deepest framework may allow a vast range of possible low-energy worlds, and that our universe is just one realized case. Some researchers welcome this shift because it may explain why certain constants appear contingent. Others see it as a retreat from the strongest form of explanation. Instead of learning why the universe had to be this way, one learns only why some universe somewhere could be this way. Whether that counts as explanatory progress remains one of the central philosophical disputes surrounding the multiverse. The inflationary route to the multiverse receives its own specific criticisms. Although inflation as a broad framework has major successes, not every scientist agrees that eternal inflation follows cleanly from it, or that the theory is as secure as popular presentations sometimes suggest. Some critics argue that inflationary cosmology has become too flexible, able to accommodate many different outcomes after the fact. Others argue that once eternal inflation is added, the theory becomes less predictive and more entangled with measure ambiguities. Public debates over inflation have made this especially visible, with prominent cosmologists disagreeing not only over technical details, but over whether the framework still satisfies the standards of a sharp scientific theory. This does not mean inflation has failed. It means that when inflation is used to motivate a multiverse, the debate extends beyond the multiverse alone and into the foundations of modern cosmology itself. The quantum route is debated differently. Many worlds does not depend on distant bubble universes, but it faces criticism over ontology and probability. Detractors ask what exactly counts as a world, how branching should be defined, and why probabilities make sense if all outcomes occur. Supporters reply that the interpretation gains strength by keeping the formalism of quantum theory simple and avoiding a special collapse rule. But because multiple interpretations of quantum mechanics often agree on observable experimental results, the dispute can become more philosophical than decisively empirical. Some physicists see many worlds as a clean reading of the mathematics. Others see it as multiplying realities beyond necessity. This branch of the multiverse debate shows again that the subject is not one single argument. It is a collection of related controversies, each with its own pressures and unresolved questions. Another criticism is sociological as much as logical. Some thinkers worry that the multiverse became attractive partly because it offers relief from uncomfortable puzzles like fine-tuning. In that view, the appeal of the multiverse may exceed its evidential support because it promises a way around questions that otherwise seem stubbornly deep. To be fair, this can happen in many areas of science. A theory becomes popular not only because of data, but because it organizes problems in an attractive way. Yet critics insist that elegance and psychological appeal are not enough. If the multiverse is to remain within science, its defenders must show not merely that it is intellectually tempting, but that it improves the balance of explanation and evidence rather than diluting it. And still, Despite all of these problems, the multiverse is not easily dismissed. That fact is itself revealing. The idea survives not because the criticisms are weak, but because the underlying pressures are real. Fine-tuning remains puzzling. Inflation remains influential. Quantum theory still invites interpretive conflict. The hope of a unique final set of laws has not yet been fulfilled. So the multiverse remains suspended in a rare position, too serious to ignore, too incomplete to accept without hesitation. It is one of those ideas that exposes the edge of science by forcing scientists to ask what counts as explanation, what counts as evidence, and how far theory can responsibly go beyond observation. Perhaps that is why this chapter matters so much. The multiverse is not only a proposal about reality, it is also a test of scientific humility. It asks whether human reason can follow its best theories into regions it may never directly see, and whether it can do so without losing discipline. Maybe the final answer will favor the multiverse, and maybe it will not. But even now, the debate reveals something beautiful about science. It is willing to dream on a cosmic scale, and just as willing to doubt itself. And as the mind grows quieter, that may be its own kind of comfort. Reality may be wider than one universe, or it may not. But in this one, at least, thought became careful enough to question its own deepest wonder. Chapter 10. What the multiverse would mean for reality, meaning, and us. If the multiverse were real, its greatest consequence would not be that science had discovered a more extravagant backdrop for fiction. Its deepest consequence would be that reality itself is larger, less singular, and possibly less final in structure than human beings have usually assumed. The multiverse, in the serious scientific sense, is not one settled doctrine, but a family of hypotheses arising from different lines of thought. In cosmology and quantum theory, some versions describe many widely separated cosmic domains, while others describe branching quantum histories. What unites them is the suggestion that the universe we observe may not be the whole of physical reality. That alone would change the emotional and philosophical meaning of science, even before any further details were settled. For most of human history, the word universe carried a kind of finality. It referred not merely to a region of nature, but to the totality of what exists. Even when science expanded that totality beyond Earth, beyond the solar system, and beyond the Milky Way, the basic picture still kept one overarching cosmos in view. The multiverse unsettles that inheritance. It suggests that what we call our universe may be only one observable domain among many, or one effectively separate branch within a deeper quantum structure. If so, then the familiar relationship between part and whole changes. We would no longer be asking only what the universe is like. We would also be asking what kind of thing the universe is, and whether our own cosmic laws and history are local features rather than ultimate ones. That possibility would alter the meaning of physical law. In ordinary scientific thinking, the laws of nature are usually treated as universal in the strongest sense. They apply everywhere and everywhen. But some multiverse frameworks weaken that picture. The deeper theory may still be universal, while the effective laws we observe depend on which vacuum state, branch, or cosmic domain is realized locally. In that case, the constants and structures we measure would remain real and objective within our universe. But they might not exhaust what is physically possible. The laws would still be laws for us, yet no longer the only way reality can be organized. This would not make science less powerful. It would make it more layered. Science would have to distinguish more carefully between fundamental structure and local realization. One of the most important implications would concern contingency. Why is the universe this way rather than some other way? Why these particles, these constants, this balance of structure and emptiness, and this long history that allowed stars, planets, chemistry, and minds to emerge? In a single universe picture, one naturally hopes that deeper physics will eventually show that reality had to be this way. In some multiverse pictures, that hope is softened. Our universe may not be necessary in every detail. It may be one realized case among many. That does not make explanation disappear, but it changes its form. Instead of seeking one unique answer to why our universe has the features it does, science may sometimes have to ask why observers would find themselves in a universe of this kind rather than another. This is where the multiverse touches meaning without becoming mysticism. The anthropic principle, in its restrained form, does not say that the universe was made for us. It says that any observed universe must be compatible with the existence of observers. In a multiverse setting, that principle becomes more than a warning against naive surprise. It becomes part of how one might understand why our universe looks unusually hospitable to complex structure. If there are many cosmic environments, most of them may never be seen from within because they do not permit stable observers at all. We then should not be startled to find ourselves in one of the rare domains where observation is possible. This does not make us central. In a way, it does the opposite. It says that our perspective is filtered by the narrow conditions that allowed us to arise. At the human level, this can feel both comforting and unsettling. It is unsettling because it weakens the intuition that our universe is the single stage on which all reality unfolds. It can make our cosmic home feel less absolute, more local, perhaps even provincial within a wider structure. Yet it can also be comforting because it places our existence inside a richer and more generous physical possibility space. If reality is large enough to contain many domains, then the emergence of complex structure in one of them may feel less like an impossible accident and more like one branch of a larger story. The multiverse does not give life a purpose in the traditional sense. It does, however, recast existence as participation in a reality whose depth may exceed every earlier boundary we drew around it. The many worlds interpretation adds a different kind of philosophical weight. In that view, the strangeness is not only that there may be other universes elsewhere, but that reality may contain multiple decohered branches associated with different outcomes of quantum processes. This does not mean that every fantasy becomes real, nor does it mean that alternate versions of you can communicate across branches. It means that the world you experience as a single continuing history may be one effectively separate strand within a larger quantum description. If that interpretation were correct, then uniqueness would have to be understood more carefully. Your present life would remain entirely real, but it would not be the whole of what the universal quantum state contains. That possibility has obvious implications for personal identity, though science alone cannot fully settle them. If branching occurs, in what sense is a future branch still you? The many worlds interpretation does not force one simple answer. Philosophically, it pressures our ordinary idea that one person must always map onto one unique future. Instead, identity may become a matter of continuity within a branch rather than singularity across all reality. Yet everyday life would not dissolve. The observer in each branch would still experience one continuous stream of memory and consequence. Practical existence remains local. Love, grief, choice, responsibility, and hope would still be lived in one experienced world at a time. The multiverse may complicate metaphysics, but it does not erase the reality of lived experience. Another consequence would concern meaning itself. Some people fear that a multiverse would make life feel less significant. If there are countless universes, perhaps nothing matters because every possibility is realized somewhere. But that conclusion does not follow. Meaning is not usually created by uniqueness alone. A sunset is not meaningless because other sunsets exist. A life is not empty of value because other lives are possible. Even in an enormous reality, your experiences remain concrete, local, and unrepeatable within the world you inhabit. The multiverse might reduce a certain kind of cosmic exclusivity, but it need not reduce importance. In fact, it may sharpen the sense that significance is something lived from within a world, not granted by the claim that one's world is the only one. This is a philosophical inference rather than an empirical result, but it follows naturally from keeping the science and the human perspective properly distinct. The multiverse would also change the tone of existential reflection. For centuries, many people have looked at the night sky and felt small because the universe is so large. The multiverse would not remove that feeling. It would deepen it. Yet it could also transform smallness into a more subtle kind of belonging. To be small in one universe is one thing. To be small in a reality that may contain many universes is another. The second kind of smallness is less about insignificance and more about scale. It reminds us that human beings were never meant to measure themselves against totality, as though totality owed them familiarity. Science, at its best, has always taught this lesson gently. The multiverse would simply extend it further. Of course, caution remains essential. The multiverse is still hypothetical. Its scientific status differs from one version to another, and many of its strongest forms face major problems of testability, probability, and interpretation. To reflect on what it would mean is not to claim that it has already been established. The responsible way to think about the multiverse is as a live possibility emerging from serious theoretical pressures, not as a solved map of existence. That caution matters because otherwise reflection turns into mythology too quickly. The most beautiful thing about the multiverse scientifically is not that it gives us final answers. It is that it reveals how far careful reasoning can stretch while still respecting uncertainty. And perhaps that is what it would mean most of all for us. The multiverse would not make us gods, and it would not make us meaningless. It would place us where science has placed us again and again, inside a reality larger than comfort, yet still open to understanding in part. It would remind us that truth does not have to feel familiar in order to be true. It would remind us that the world we know may be only one clearing in a forest of possibilities, and that even one clearing can hold warmth, memory, love, and thought. If other universes exist, they do not diminish this one. They make it more astonishing that, in at least one region of reality, matter became calm enough to wonder where it was. And as the night grows quieter around you, that may be the gentlest conclusion of all. Whether reality is one universe or many, you are here, awake for a brief moment inside it, and the fact that anything can know the cosmos at all remains one of its softest miracles. And now, my friend, as this vast idea begins to settle into the quiet corners of your mind, you can let it drift gently into the background. Whether the multiverse is real or only a possibility, it reminds us that reality may be far larger, deeper, and more mysterious than it first appears. If you are still awake, you can stay with me and explore another calm journey through science. But if sleep is finally beginning to find you, then let go of the day. Close your eyes and rest easy. Sweet dreams among the stars.